All right. So today we're going to be talking about chapter 5.3 in your book. It is all about exponential functions. Most of the time, we're going to be looking at interest rate or interest, which is actually something that's really applicable to the rest of your life. So it's some useful information, actually, which not that the stuff in this class isn't useful, just that a lot of it won't be used by most of you, but this definitely will. So yeah, we're going to jump right into this. It's probably going to be a little bit on the longer side, so I apologize ahead of time. But first, we need to define what an exponential function actually is. So first of all, let's look at the difference between linear functions and exponential functions. This right here is a linear function. As you can see, every time x goes up by 1, we have an increase, in this case of 2, in our f of x, or what would be our y value if we're thinking about it in y equals mx plus b terms. Then if we look at the data table for an exponential function, you're going to notice that it's a little bit different. Here we go from 3 to 6, then we go from 6 to 12, and then we go from 12 to 24, and then 24 to 48. So what we're seeing is each time here, we're multiplying by 2. And this is a little bit different. If you tried to find like some kind of x squared function to fit this, you wouldn't be able to do it. This is actually what we call an exponential function. So the general form of exponential functions is f of x equals c times a to the x. In this case, c is the constant. And one of the things to look for is that f of 0 is always going to be equal to c. We'll talk about why that is in just a minute, but that is an important thing to note. A is the base. So if we think about a power, it always has a base and a power, and then x is, of course, going to be the power in this case. And it is the factor by which f of x is multiplied for each increase of x. In general, a true exponential function will use only positive numbers for both the constant and the base. And this is for a few different reasons, but that doesn't really matter right now. What does matter is that we can derive some formulas from it. So first and foremost, let's fill out a data table for the following function. Now, I told you already that f of 0, which will be what we have right here, is always equal to whatever the constant is. So in this case, we know it's going to be 3. But why is this 3? Well, if we plug in 0 for x, we have 3 times 2 to the power of 0. And hopefully you remember that 2 raised, or anything raised to the power of 0 for that matter, is equal to 1. So 2 to the 0 equals 1. We have 3 times 1. Boom, there we go. That one's done. Then what we're doing is, next up we have 3 times 2 to the power of 1. 2 to the power of 1 is, of course, just 2. So we have 3 times 2. That's 6. Then we've got, let's see, 3 times 2 squared. 2 squared is 4. 3 times 4 equals 12. Now, you might already be noticing the pattern that's coming here, but we're going to go ahead and do these all out anyway. When we plug in 3 for x, we get 3 times 2 to the third. 2 to the third is 8. 8 times 3 is 24. And then the next one, we have 2 to the fourth. That's 16 times 3. That's 48. And 2 to the fifth is 32. 3 times 32 is 96. You'll notice that each time, once again, we're going up by 2. Now, the number is not always going to be 2. I just happen to use the same formula that we were using in the table before, so that we can get back to the same place. But we'll see in just a little bit that you can use all sorts of different values for your a, and that will create different multipliers. So let's look at this one. This time we have f of x equals 64 times 1/2 to the x. Now, you'll notice that this has a negative value for our x. So we can have negative exponents. That doesn't make any difference. What we don't want to have is negative values here. And the reason for that is if you think about a graph of like a function, right? You have a bunch of different decimal points in your function. Now, let's say we had negative 3 raised to the power of x, right? We can do negative 3 to the first. We can do negative 3 to the second. We can do negative 3 to the third. You'll notice something a little bit weird about this. If I do negative 3 to the first, it's negative 3. If I do negative 3 squared, that's 9. If I do negative 3 to the third, that's negative 27. So we're flipping back and forth between negative and positive. More importantly, though, somewhere on this function would be negative 3 to the 2 1/2. Now, -3 to the 2.5 is something we actually can do. We know how to do this now. You might not be able to easily off the top of your head think about it, but 2.5 is basically equal to 5/2. And you can do this. If you paid attention to chapter 4.8, we talked about how to do something like this. We take the square root of -3 and we raise this to the power of 5. Here's the problem though. -3, the square root of -3 is in fact I. Well, it has an I in it. It's not just I, but the square root of -3 has an I somewhere in it. If we take I and we raise it to the power of 5, that's going to give us I to the 5th, which as we know from chapter 3 or something, I don't remember where this part was, but I to the 5th is just equal to I, which means that our final answer for this will have an I somewhere in it, and we can't graph that. So this function can't actually be graphed if we have a negative number for our A value. We can use a negative number for the C value, but generally speaking, that doesn't represent any real data, so there's no real reason to do it. Anyway, that was a long-winded explanation to just talk about why this is. However, we can do negative exponents. So we're going to start with this one. We have 64 times, and then we're going to have 1/2 to the -2. Now, when we take a number to the negative power, a lot of people got this wrong on the test, so I'm going to go over it again. If you don't know how to do this right now, please review exponents a little bit. If you want to talk about it in class, that's perfectly fine. I'm not going to do it entirely in this lecture because it's already going to be long enough. But when we're raising something to a negative power, what we're basically doing is we're flipping it and then raising that to the same power. So in general, you're going to be doing this. Like if you have 3 to the -2, goes to 1/3 squared. In this case, since we've got 1/2, we're going to flip it. We're going to have 2/1. These are both squared, but 1 squared is 1, so we just get 4. So 1/2 to the -2 is equal to 4. 4 times 64 is what, 256? So this is 256. Now, luckily, doing 1/2 to the -1 is super easy. We just flip it. So we'd have 2. 64 times 2 is 128. I've already told you before that f of 0, whenever you have an exponential function, is going to be equal to whatever your constant is. In this case, that's 64. And then we start plugging in positive numbers that are a little easier to work with. So first of all, let me erase some of this stuff so I have room. And then we'll do all the positive ones. So first, we're going to have 64 times 1/2 to the power of 1. 64 times 1/2 to the 1. Obviously, 1/2 to the 1 is just 1/2. 64 times 1/2 is 32. Now, we could continue filling in this table with just by using the pattern from here. You can already see what this one is. It's times 1/2 every time. Times 1/2, or divided by 2, whichever way you want to think about it. Doesn't really matter. But we're going to go ahead and solve this out the long way. So we have 64 times 1/2 raised to the power of 2. 1/2 to the power of 2, we have 1 squared, which is 1, over 2 squared, which is 4. So this is equal to 64 times 1/4. 64 divided by 4 is, of course, 16. And by of course, I mean, you might have to do division for that. I don't know how many of you would know that off the top of your head. I know it because I've already filled this in. Anyway, and then we're going to do 64 times 1/2. Whoops, 1/2 to the 3rd. 1 cubed is still 1. 2 cubed is 8. So we have 64 times 1/8, which is equal to 8. So there we go. We were able to fill in this chart here. Really quick, obviously, this doesn't just have to be a value of 2. You could have done like 2/3 in here. You could have 3 in there. You could have 4 in there. It doesn't matter. But whatever is in here is going to be the number you're multiplying each f of x by to get the next one, assuming you're going up by 1. We can also determine exponential functions based on a couple of given points, assuming that we're told that it's an exponential function. If I just told you that there was a function with f of 0 equals 3 and f of 2 equals 12, this doesn't necessarily mean that it's an exponential function, right? Like this could be 4.5. Yeah, this could be 4.5x plus 3. that would also satisfy these conditions, but we're told that it's an exponential function here. So we're looking for a c value and an a value, and we know that it's ca to the x. So for both of these, f of x equals ca raised to the x. Now, I've already told you this is something important to keep in mind. C is whatever value f of x is equal to when you take the f of 0. So in this case, the first one for a, f of 0 equals 3. That means that c is equal to 3. That part's easy. That's already done for us. So we have f of x equals 3a to the x. Now, we've also got a 2. We know that f of 2 equals 12. So that means that we can plug in 2 for our x. So 3 times a squared equals 12. And then we can divide both sides by 3. So we get a squared equals 4. And then we take the square root. Take the square root. Those cancel. And we have a equals. Now, from previous chapters, we've talked about this could technically be positive or negative too, but I already told you that you can't have a negative value for a. That doesn't work. So it's just going to be positive 2. So that means that our formula for a is f of x equals 3 times 2 to the x. All right, then for b, this one's a little bit trickier. We aren't given f of 0, so we can't start out by calculating c. We're going to want to calculate a first. And the way to do this is when we go from f of 1 to f of 3, that is effectively a difference of x equals 3. So a cubed is equal to, and then we divide it by 1/8. So 1/8, right? To get from here to here, we divide it by 8. A cubed equals 1/8. That means that a equals the cube root of 1/8. The cube root of 1 is 1. We're just taking the cube root of both sides, by the way, to solve this. Cube root of 1 is 1. The cube root of 8 is 2. So a equals 1/2. Right, so all I did here was say, okay, a to the whatever the difference is between f of, this is -1, this is 2, 3 equals, and it's this one divided by this one, so 1/8. So like if I had f of -2 equals, I don't know, let's say 2, and f of 2 equals, let's go with 16, right? I would do in this case a to the 4th equals, and then I would do, actually let's make this 32 because that'll actually work. 32/2 equals 16. So a to the 4th equals 16, and then we'd want to take the 4th root of both of those. But anyway, so a equals 1/2. So now we're left with c times 1/2 to the x, and then we can just plug in either of these values, the -1 or the 2. I'm going to go ahead and plug in 2. So we have 2 times 1/2 to the, or wait, oops, sorry, we plug in one of these values for x. That's why I was confused. That didn't make any sense. Let's go back, ignore that. So we're going to plug in 2 for x, not for c. So we have c times 1/2 squared equals 1. 1/2 squared is equal to 1/4. So 1/4 times c equals 1. Multiply both sides by 4. This will cancel. And we're left with c equals 4. So we get 4 times 1/2 to the x. In general, we want to put this one in parentheses, both to separate it from this 4 and also in order to raise it all to the power of x, just to avoid confusion, because somebody might, for instance, think that I was saying 1 to the x over 2 or something weird like that. So we just write them in parentheses next to it and with the x on the outside. Okay. Now we're going to talk about interest. So generally speaking, in this class, I've avoided doing a lot of story problems. But this one, we're going to go directly into story problems, and that's most of what we're going to focus on, just because this is something that's actually going to be really relevant to you for the rest of your life. In general, interest things are calculated for you, but it is something that you'll want to be able to calculate on your own for things like house payments. And then the example we're going to use here is a retirement account, but if you're getting a loan for a car, or if you're getting a loan for a house, whatever else. So interest is generally a percentage of money gained over a given period of time. Hopefully you guys already know what interest is. It can be applied to loans, it can be applied to investments, it can be applied to whatever else. The initial amount of money put in is called the principal and is abbreviated P. So the principal can be like if I invest $1,000 into an account, that's the example we're going to look at in a little bit. That's the principal amount. If I take out $35,000 of school loans or student loans for a master's program, that's the principal amount of my loan. And then the interest will be calculated based on that. If you take out $350,000 for a house loan, then the principal is $350,000. The rate of interest is usually a percentage, but it's always going to be expressed as a decimal when we're doing calculations with it, is abbreviated R. And the amount of time the money is accruing interest is abbreviated T. Now, the simple interest formula is also known as interest that's compounded annually. So basically, we take the amount of money that we have in there, we multiply it by the rate, whatever the rate is that your interest is collecting at. And if it's compounded annually, or if it's called simple interest, then that means you do it at the end of every calendar year. So if you've left it in for 1 year, you multiply it by whatever the percentage is, and you add that amount in. The formula for simple interest, or interest compounded annually, is the amount at the end equals your principal times 1 plus R, all raised to the power of T. Now, I could derive all of this for you, and if you want to see that in class, I'd be happy to do it. But right now, that's just going to take a lot of time. It's not worth doing. So we're not going to bother with that at the moment. So we just want to know this formula. A equals P times 1 plus R raised to the T. If you're taking notes, write this down 100%. You're going to need it on your test. You're going to need it on your homework. That is definitely something you want. So let's suppose at age 20, you invest $1,000 into an IRA that pays 12% interest compounded annually. Now, this is unrealistic for a couple of reasons. First of all, no IRA pays a guaranteed amount of interest. That's ridiculous. It'd be awesome, but that doesn't happen. 12% is also very, very kind. Generally speaking, if you know what you're doing with an IRA, you can expect around 10%. But eventually you're going to get taxed and stuff, and it's a whole bunch of other different things. But this will work for our example problem. What you could do is, if you wanted to, you could do these calculations on your own with 10%, see what that looks like. And trust me, this is going to be kind of cool. But we're compounded annually in this case. For the most part, interest is going to be compounded monthly when you're doing IRAs, I believe. But it does depend on what your IRA is in. Anyway, so the question is, how much money will be in your account in A, 10 years, B, 20 years, and C, 45 years? So this would make you 65 if you invested at age 20. 20 plus 45 is 65. That's the normal retirement age. So first of all, we know that A equals P times 1 plus R raised to the T. In this case, our P is 1,000. So we're all of these problems are going to start with 1,000 times 1 plus, our rate is 12, but remember that's expressed as a percent. So 0.12 raised to the T. I'm going to simplify this. 1,000 times 1.12 raised to the T. Okay, so then I would strongly recommend using a calculator for this, which I don't actually have ready. So let me get my other computer opened up, because I wasn't thinking ahead. But for 10 years, we're going to plug in 1,000 times 1.12 raised to the power of 10. And in just a second, when I have a calculator, I'm going to show you what the answer is to that. Then we're going to do 1,000 times 1.12 raised to the 20th power, and then 1,000 times 1.12 raised to the 45th. And apparently my calculator is not going to be ready anytime soon, so we're going to do it like this. So we've got 1.12. On a graphing calculator, this is super easy. Shouldn't take you very much time, but I was not prepared. So the first one, after 10 years, this should be worth $3,105.85. So that's our answer to A. which is not bad. You don't have to do anything to accrue this interest. So, 10 years later, you've got $3,000 when you started with just 1,000. That's pretty good. Then we're going to look at what happens in 20 years. So after 20 years, we plug this into a calculator. We're going to have $9,646.29. So also not bad, right? 20 years, you didn't do anything. You gained what, $8,646? It's, not great, but it's not nothing. Right? And then we're going to look at what happens in 45 years. So 1.12 raised to the 45th times 1,000. Now this is where things start to get a little bit crazy. But after 45 years, this is going to be worth $163,987.60 without doing a single thing. So this is not necessarily just an ad for you guys to all go out and invest early, but this is the power of interest that compounds on top of itself. Right, now the reason for this is obviously that after the first year, right, if we have $1,000, we gain 12% interest. All we're gaining in the first year is 120 bucks, right? So now we have 1,120. But then the next year, 12% of 1,120 is $134.40. So now after 2 years, we have $1,254.40, right? And then 12% of that is bigger than it was before, and so on and so forth, until eventually you're making actually quite a bit of money every year just by getting your 12%, right? So 12% of this one is going to be like what? I mean, well over $1,000, right? So this time, every single year, you're making more money than you started with, which is pretty cool. Now, real interest isn't quite usually that simple. Most of the time, interest is not compounded annually. Interest is often compounded quarterly, which means it's done 4 times a year, or monthly, which is 12 times per year. Those are the two most common, but it can be on any other period. We're going to talk about one other period in just a little bit, but in general, quarterly and monthly are the 2 times, or the 2 ones you're going to see the most. The interest formula can be adjusted to reflect these new compounding periods, and we abbreviate the compounding periods as n. Right, so if there are 4 periods in a year, n equals 4. If there are 12 periods in a year, n equals 12. The new formula, again, is something you're really going to want to write down. This is for compound interest. Oh, it's up at the top. I'm not going to bother writing it again. So simple interest, this is compound interest. A equals P times 1 plus R over N raised to the NT. Again, this is something that if you're interested in the derivation of, we can go over that in class, but this lecture is going to be long already. I don't really want to take up more time with this. So let's look at how to use this in calculations. I'm going to write this down at the top while it's still fresh in my mind. A equals P times 1 plus R over N raised to the power of T. Now, so it says, suppose that at age 20, you invest $1,000 into an IRA that pays 12% interest. Okay. How much will your account be worth in 10 years compounded quarterly, 45 years compounded quarterly, and 45 years compounded monthly? Now, just for the sake of reminding everybody, let's go back here. So in 10 years compounded with simple interest, this was worth $3,105 and something. Right? Let's see how much more it's worth if we're compounded quarterly. So if we do this one, we're going to plug in 4 for n. We're going to use all the same numbers like we did before. So we're going to have, in this case, A equals 1,000 times 1 plus. This time we have R, which is 12, over n, which is, or sorry, R, which is 0.12 over 4, times 4 times 10. So we plugged in n, and this was R, this was T. Right? We just used this formula up here. Okay, now this simplifies to 1,000 times 0.12 divided by 4 is 0.03. So we have 1.03 all raised to the 40th power. So then once again, we plug this into a calculator. We're going to get 1.03 raised to the 40th. So 1,000. So our new value, A equals $3,262.04. So it's not a huge difference. It's another, what, $157 just because it was compounded quarterly. Now you might ask, why is that? The main reason, you're getting the same amount of interest per year, but now what you're doing is at the first year or at the first 3 months, you're getting 3%. So you'd gain $30 at the first period. And then you have a little bit more in the account when you take the interest the next 3 months and then the next 3 months and the next 3 months. So you're just building on it a little bit more often. So as you can see, the shorter your period is, the more interest you're going to get. So now let's look at the 45-year mark, this time compounded quarterly. So this time we have A equals 1,000. Our principal is the same. I'm going to just leave this as 1.03 because I don't really want to redo this part of the simplification. And then we're going to have 45 times 4, n times t. N is 4, or yeah, n is 4, t is 45 this time. 4 times 45 is 180. So we're going to put that there. All right. So we take 1.03, we raise that to the 180th power, and then multiply it by 1,000. And this time we get A equals $204,503.36. Now, just to compare that to our value before, originally we had $163,987.60. 163,987.60. So this is like a $40,000 difference, a little bit more than $40,000, just because we compounded it quarterly. Now let's see what happens when we compound it monthly. So we're going to have A equals 1,000. This time we have a different n, so we're going to need to do our formula from scratch again. Plus we have 0.12, that's our rate, divided by 12, which is our n. And that's all raised to the 12 times 45. Now 0.12 divided by 12, that's 0.01. So this time we have 1,000 times 1.01 raised to the 12 times 45 is 3 times 180, which is 540. So 1.01 raised to the 540th power times 1,000. So this time, if we have 45 years compounded monthly, A equals 215,546.93. So as you can see, the more often you compound your interest, the more money you get at the end. Right? When we compounded it annually, we had $163,987.60, which is still quite a bit. Then when we did it quarterly, we had $204,503, and then when we compounded it monthly, we had $215,546. So obviously, the rate is more important than how often it's compounded in general, but both things are really important. And getting a rate, if you have the same rate that's compounded more often, that is going to be better for you in the long run. Now, you might be wondering, what happens if we compound something closer and closer and closer to continuously? We could do it daily, we could do it hourly, or we could even do it once per second. Now, this is a really complicated number to arrive to, and it took one dude back in a long time ago. This is actually pronounced, I think, Euler is how this is pronounced. It's a weird name. But if you derive this out, if you ended up compounding interest continuously, so you were just compounding interest every possible moment you compound it, you end up getting the formula that looks like this. So it maxes out at around 2.71828182846 raised to the rate times time, this is in years, times what you start with. This number, like I said, really hard to come to. I can show you a little bit of it. I don't actually know the full derivation of this number, but this number, luckily, is in your calculator as E. So that's why this is titled the number E. When you have continuously compounded interest, your continuously compounded interest can be calculated using the formula A equals P times E raised to the RT. Now, all the other numbers are the same. This is still principal. This is still rate. This is still your time in years. And now E is just a value that's actually in your calculator. And even my phone calculator has E in it. Your graphing calculators definitely do. If you, for some awful reason, like if you're going into an accounting major or something like that, if you ever have to use E as a number itself, usually we approximate it as 2.718, sometimes 2.72. But in general, you're going to want to use a calculator for these kinds of things. So let's look at doing this. We're going to do another one, same exact amount of money, but we're going to see what the absolute maximum we could possibly get with this rate of 12% is. So we're continuously compounding. We're compounding at every possible fraction of a second you could possibly compound it. And we're going to look and see the same values that we calculated the original time. Now, remember the first time we had like 3,100, something around there. This one was like 9,400 and something. And then this one was 163,000 and whatever. All right, let's see how much it is when we compound it continuously. So remember, the formula is, a lot of people just say A equals PERT. It's the PERT formula. I don't know why. I mean, obviously I know why, but it's P times E raised to the RT. Just remember that only E is being raised to the RT. If you multiply it out, you're going to like your answer a lot better when it's money like this, but it's not going to be correct. So in this case, after 10 years, we've got A equals 1,000 times E to the power of, and then we have 0.12 times 10. So that's 1,000 times E raised to the 1.2 power. So we're going to hit E raised to the power of 1.2, and then multiply that by 1,000. And we get about $3,320.12. So, it's about $220 more, not too bad. Then we're going to go ahead and plug in 20. So we'll have 1,000 times E to the 0.12 times 20. That's equal to 2.4. So 1,000 E to the 2.4. So we take E, raise it to the power of 2.4, and multiply by 1,000. This time, we're going to get $23.18. So we got about, a little under $2,000 more this time. We're up to 11,000. The initial, when we compound annually, we're just down around 9,400. I don't remember the exact number, but it's somewhere around there. Right. And then for the last one, $1,000 invested when you're 20, when you retire at 65, it was magically compounded every second, is 1,000 times E raised to the 0.12 times 45. This time I'm going to let my calculator do that for me. 0.12 times 45. Okay, 5.4. So we have, I haven't used the X button. So this one gives us, and you can actually plug it into a graphing calculator exactly like this, which is really nice. You just do 1,000 times E little caret to 0.12. It's 45. I'd put this in parentheses. But what you're going to get when you solve that out is $221,406.42. So this is the absolute maximum you would have in 45 years, having just invested $1,000 at a rate of 12. Now, really quick, before we finish up, I want to compare that to if we compound monthly. You'll notice that if we compound it monthly, we're already at 215,500. This only adds another like $6,000, right? Compared to the initial, which was around 163. Like, it's not as big of a difference. Compounding monthly is a really big difference from compounding annually, but beyond that, it doesn't make as much of a difference. So generally speaking, compounding annually is going to be the best for you. Unfortunately, credit card debt also compounds annually or monthly, and that's not as good. We don't want that. But anyway, that's it for this lecture. I know this information is kind of a lot more like working with powers of X and stuff is a little bit more complicated. But hopefully the homework won't be too bad on this one. And I think that this information is a lot more useful for your actual everyday life. I'll be happy to take some questions in class, and I will see you guys later.